This work is based on many collaborators, and one of them is here, Professor Mikyung. Couldn't find him with Samir right here. And today I will talk about the cloaking, and the previous talk was about cloaking. Even my talk is about cloaking. I have just one C in my outline. So, yeah, first I will explain what is the cloaking and the near-cloaking, and explain the GPT and how to use the GPT to enhance the cloaking effect, and then move to Helmholtz equation, and then I will finish with the full Maxwell equation. The cloaking is to hide from the measurement. For example, in the movie The Harry Potter put the invisibility cloak, and people couldn't see him. Like this, I want to make some structure, and when we put something inside, that object is invisible. The inside object and also the cloaking structure. Before I explain the cloaking, I will start with the imaging problem. Here the governing equation is the conductivity equation when sigma is conductivity profile, and when we use the measurement, the Dirichlet to Neumann map, that means we have the voltage and current on the boundary. Then can we reconstruct the sigma? It is the imaging problem. So from the measurement to get the sigma. But that question is not well posed. It means in the sense that it doesn't have the uniqueness. Suppose F is a diffeomorphism of omega, which is identity on the boundary, and put the F star sigma, which is the push forward, defined as Jacobian matrix times the conductivity times Jacobian matrix transpose divided by its determinant. In that case, the measurement on the boundary is the same. So even we have two different conductive profile inside, from the voltage and current measurement, these two structures are not different. I mean, the measurements are exactly the same. And the extreme case is for one sigma, I have just identity, and in identity on a ball with radius 2, and let's say it has just 1 point exception. So the first structure is a ball with a conductivity 1, and the other one is the F star 1. Now here, F is from the ball to the annulus, and since the measurements are exactly same, from the measurement we cannot distinguish this one homogeneous ball and the other one with something hidden inside. So things inside the unit disk are cloaked, and but this structure is not physical. That means if we want to really make that cloaking structure, I should have materials which has this parameter exactly same as F star 1. But this F star 1 is singular. It means in some direction the directional conductivity should be infinity, and the other direction is 0. So you couldn't make it physically to have some structure which has this anisotropic material property. Then how can we make it realistic? The thing is, F star 1 becomes singular because we blowed up a point to a unit disk. So here is the new cloaking idea. So the cloaking effect is not perfect, but the F star 1 is no more singular. I mean, so to do this, for the diffeomorphism F, I send a disk with a small hole here. Except the small hole, the conductivity is 1. The extreme case was rho equals to 0. But now take the small rho, small but positive, and then take the diffeomorphism F. Then the difference between the two measurements, one is the homogeneous case, the other one is this cloaking structure, has the difference in the measurement smaller than some constant times rho squared. So the extreme case, rho equals 0, it gives the perfect cloaking, but for that case, F star 1 is singular. So instead of blowing up a point, I'll blow up a small ball with radius rho. Then the cloaking effect's not perfect, but small as rho squared. So this is the near cloaking idea. But how do we have this rho square? If I expand lambda sigma, when sigma is 1 except the small radius ball, then the difference between the homogeneous case and sigma is that the leading order part is the gradient of background solution times the some number depends on the size of rho times gradient of Green's function for the conductivity. So if you look at this M, then it has the size rho square. That's why we have the difference between lambda sigma and 1 by rho square. So if we have some structure which has this polarization tensor to equals to 0, then the cloaking effect will be better than rho square. Because the leading order term is rho square, in the case m equals 0, the cloaking effect is enhanced. The first idea you may think is to take some shape other than a ball. But with that different shape, even we took arbitrary different shape, we couldn't make m equals 0. Here is the bounds for this polarization tensor for a simply connected domain, and there is the upper bound and lower bound. So this m should be inside some certain region, and it couldn't be 0 at all. So it's not possible to make m 0 with a simply connected domain. So you can think layered structure. So here is the neutral inclusion of a Hashin. When we have two layer structure, by putting some elastic parameters, then when we put uniform field, the perturbed wave is 0 outside this two-layer structure. So I want to make a structure similar to this Hashin's neutral inclusion. So adding some layer and make m to be 0, and that enhances the cloaking effect. So let me take a closer look on the expansion of the potential solution. Here, previously I explained the model on the, with the measurement on the boundary. Let me change it to be the exterior problem. So when sigma is 1 outside an obstacle and has conductivity gamma inside an object, and without this omega, then the some constant vector a times x is the solution to the conductivity equation, and then in the case we have some obstacle, then u is the background solution plus perturbation, and in that perturbation, the reading order part has this polarization tensor that I explained before. And to understand, to make some enhanced cloaking structure, let me go further to further expansion, so rather than stop at its first order polarization tensor. So here is the full expansion. So when H is the given background solution, then the perturbation has expansion given by the background solution derivative at the origin point, and derivative of fundamental solution for the Laplacian, and some number depends on the obstacle omega. So U has U equals to the background solution times the polarization tensor times the derivative of gamma. So here the MR per beta explains how the omega influence on this perturbation, because H is independent of omega. It's this given entire solution. Gamma is a fundamental solution. So the MR per is the only MR per depends on the obstacle domain. So now you can think that in the case we can measure the perturbation and get this MR per beta, then how this MR per beta is related with the shape or the material property of omega. The first order term is a polarization tensor which has one-to-one correspondence between the ellipsoid in 3D. So this M is 2 by 2 symmetric matrix, so it has 3 information. So it tells the angle of the ellipsoid and its magnitude. So with the first order term, we can have the equivalence ellipse, and the ML per beta also have the geometry information of omega more than just the ellipse or ellipsoid shape. So for example, when we take the energy function as the difference between this ML per beta of our target domain and the measurement, the data from the measurement, and then doing the minimization process, actually it gives very good information on the shape of an obstacle. For example, here GPT of the order 2 is ellipsoidal shape, and up to 3 and 4 here the final shape is up to 6. Then it's quite well represent the target shape. So until now,
so if
yeah.
you increase the iterations,
Yeah.
they eventually will converge to the actual shape.
But to do that, we should have we should have the M alpha beta to high order, and it's quite unstable if the number goes up. And to do that, you need very good computation skill, and yeah. For me, 6 is the 6 or 7 is the maximum number I can handle it. Yeah. So yeah, here. So I explained that the M alpha beta is the coefficient in the expansion of U due to the obstacle, and when you have this M alpha beta, then it gives you quite good approximation in the shape. And we can also tell the topology change for GPT up to 6. Actually, we can separate the inclusions. But don't forget that my talk is about the cloaking, not imaging part. So how can we relate this imaging? That means from some given measurement to get the to get information of target. And how can relate this imaging to the cloaking problem? The cloaking is to hide to the measurement, and imaging is to reconstruct the unknown target. So up to now, I explained how to get the target shape when you have the GPTs. By getting GPTs up to high number, you can have more detailed shape of an obstacle. So now let me explain more about the GPTs. Before I explain with this the M alpha beta, which is related with the polynomial order, but by taking the harmonic sums, that means A alpha times X alpha are harmonic polynomial, then the expansion becomes even simpler than the first one. So if we take the harmonic sums, then this harmonic sum tells you for a given the entire solution, which has the 3 mode expansion, then how the quotient influenced from this age and obstacle. So in the near-cloaking structure I explained, I'll use concentric discus. So for that case, this the concentric discus are 0 if the sub-index different, and also is 0 when we take the cosine or sine quotient. So the only the term we need to consider is the m's of nn of cosine cosine or cosine sine. So I will say it is m sub n. At first I told you that when you blow up a small disk, then the difference in the measurement from the homogeneous case is m times rho square. So, but actually, using the full expansion of the perturbation of U, we have high order expansion. So in the reading order part, there is m m sub alpha beta, and alpha plus beta order is 2. then it's multiplied by rho square. But if you use the full expansion, then here comes the expansion. The reading order term is m square, rho square, and then you have rho 4th and rho 6th. So the higher order term is some number times rho to the 2k times m sub k, and that tends to depends on the conductivity profile. So to make this m to be 0, so without doing anything, the m couldn't be 0. But by adding more and more layers, and then choose the sigma in a nice way, then this mk could be 0. So add more and more layers, I can more flexibility to decide the sigmas, and then mk could be 0 to the higher order. So the enhancement of near-cloaking is possible when I take a sigma such that mk is 0 up to some order. So for that case, the now cloaking effect becomes rho to the 2n plus 2. So without doing anything, the n is 0, but when you take m to be 0 up to higher order, becomes the power of rho becomes 2n plus 2. But how that is possible? So my cloaking structure is concentric discus, and the unknown is the radius of each layer and the conductivity on each layer. So the unknown is sigma j, and the exterior conductivity is assumed to be 0. And I want to make it insulated in the inner layer. That's why because the object inside the layer should be cloaked. That means it should not influence the perturbation outside. So I want to make it insulated, so the current couldn't go inside the inner layer. So I put sigma inner layer to be 0, and then get the numbers such that the exterior measurement to be 0. So on each layer we have two boundary conditions. One is the Dirichlet condition, and the other one is the Neumann condition. So on each layer it has two boundary conditions. It becomes 2 by 2 matrix, and since we have n plus 1 interface, the exterior coefficient and inner coefficient has the relation with this matrix multiplication. And then the mk tells you how you have the perturbation when the incoming wave is assigned. So this mk is the perturbation, the coefficient in the perturbation part. So now we know how to get this mk when the conductivity is given on each layer, and then doing the optimization. So for each iteration, I have this mk from the matrix multiplication, and then I have this mk, and then get the directional derivative, and just state sigma by sigma minus A inverse times B, and then you have this result. So here, this one is the cloaking structure to make M to be 0 up to K equal to 3. With a 3 layer, and then doing the optimization, we have those numbers, and then the MK is 0 for 1 and 2 and 3, and also for M is 6, and with 6 layers, and the connectivity. Here y-axis means the connectivity on each layers. It gets more and more singular actually when you make a cloaking effect better. And here is a numerical test. The first blue one is the cloaking effect without layer, just blowing up a small hole. And the second one is the small hole and add one more layer to make M to be 0 for case 1, and add one more layer, that is a green line, and then the rho sigma is the cloaking effect. That means the difference between the boundary measurement of the homogeneous case and the cloaking structure case. So the idea, when rho is 0, then it was just 0, but without but when we blow up a small ball, then this cloaking effect was rho square. Now let's see how the effect is enhanced. The first black line is the cloaking without adding layer, and then the blue one is the the blue one is the blowing of a small hole, and red is with one layer, and green line is with 2 layers. You can see that the cloaking effect gets better when you add more layers. So this is the connectivity equation case. The idea is extended to the Helmholtz equation. So now the equation we consider is this equation with electromagnetic parameters, and I consider the far field measurement case. So before the measurement I use is on the boundary, but here is the so-called far field pattern. So when we have some obstacle, and then and U is the background solution. So it satisfies the Helmholtz equation outside. And for example, if I use the plane wave, which is exponential of ikx, and k inner product k is omega square times the material properties outside the cloaking structure. Then we have this expansion with this far field pattern. So when the background solution is assigned, the solution is perturbed. The perturbation is exponential times exponential divided by square root of x magnitude times the far-field pattern. It depends on the direction of the incoming wave, background solution, and the direction of the x value. So the measurement location. So so here how can we have some structure such that the perturbation is small, even we have something hidden inside the structure. So the object is to make the far-field pattern A to be 0, even this obstacle D is not small. Let me first start with the expansion with the Bessel function. I said we use the plane wave for the background solution, and this plane wave has the expansion with the Bessel function, the exponential times Bessel function times exponential, and the fundamental solution to the Helmholtz equation is the Hankel function about the 0, and when you put x minus y in the fundamental solution, it has this the separation. So Hankel function with x times the Bessel function in y. So with this separation, we can prove that the perturbation due to the obstacle is some function depends on x times coefficient w and m times exponential function. This exponential depends on the direction of incoming wave. And as I said in the conductivity case, if we make this coefficient, I say this W and M is scattering coefficient. If we make this coefficient to be 0, then the difference between the homogeneous domain and the cloaking structure, the difference of measurement is very small. So now to make the here the far-field pattern to be very small, I will construct some layered structure which has very small scattering coefficient W and M. So W and M is defined as the boundary integral with the density satisfying this system. One is about the Dirichlet condition. The other one is the Neumann transmission condition. Yeah, here, so the far-field pattern equals to summation of some angle, exponential of angles times W and M. So by making W and M small, the far-field pattern is small as well. As before, if we take the push forward of the material parameters, which is identity away from the origin, then the far-field then it satisfies the same type of equation, the Helmholtz equation with alpha star mu with alpha star epsilon instead of mu and epsilon. And since it's identity outside, the far-field patterns are coincide. So for mu and epsilon and it's pushed forward, the far-field pattern A infinity are the same, and we use a cloaking structure which blows up a small balls. So for to get this mu epsilon omega, which is almost identity, but except a small concentric discus, I said this mu epsilon is mu tilde psi of 1 over rho. This psi is 1 over rho times x. That means it changed a lot when x is very small. See, so so this mu tilde of psi 1 over rho means we use a small concentric discus, and actually you can prove that for these material parameters, actually the far field pattern equals to mu tilde mu epsilon tilde times rho omega. So when the frequency omega is fixed, actually what we care about is the far field pattern with rho times omega, and rho is a small number. So when frequency is fixed and take rho very small, then rho times omega is small number. And in the following slide, I compute the Hankel functions and Bessel functions for rho frequencies. So for the rho frequency asymptotic of Hankel and Bessel functions, the scattering coefficient, you can show the scattering coefficient are bounded by rho to the order n plus m, and we to make w to be small. And since when the subindex goes higher, it's bounded by rho to the high number. So what we need to care is w and m with small number, with small n and m, because for high number by itself is small enough. So I just care about w of leading orders. And when we use concentric discus, the cloaking device I suggest is the concentric discus. And for that case, w and m with different numbers are 0. So I only need to care w and m when n and m are the same. So the structure we look for is such that WNN is small o of rho to the 2n. As before, the unknown is the radius and the material parameters mu and epsilon. From the two transmission condition on each layer, here is the 2 by 2 matrix times the coefficient equals to the matrix times the coefficient. And on the inner layer, I put the Neumann condition, and then Wn comes from this matrix P, which is the multiplication of the transmission conditions. And since rho is small number, and the frequency we consider is rho times omega, so the so we need the expansion for the small parameters. And when t is small, the Bessel functions have this asymptotic expansion. So using this, I have that the scattering coefficient is T is rho times omega, which is assumed to be small, is T to the 2n times high order expansions. So now the problem is to make a structure such that this coefficient Wn tilde to be 0 up to some order. And here is the result. When I blow up a small ball, then W is not 0. It is like it's order 1, but by adding one layer, then you can see that W of the coefficient in the Wn becomes small. So the Wn, the first one is without any layer. So and then we have one layer and two layer structure. And for the structure I suggested has much smaller scattering coefficient. And it can also extend to the full Maxwell equation case. And in all three, and E and H has a coupling which satisfies this Maxwell equation. And as before, with pushing forward the material parameters, you can have that the scattering amplitude is the same for mu and epsilon, and for the pushing forward parameters. And then it has more complicated expansion. So using the multiple solutions of Maxwell equations, the perturbation is expanded with this coefficient. Now it has the transverse electric or transverse magnetic, so the index gets more complicated. But the idea is same. To make the perturbation to be very small, the structure I need is the one which has a very small coefficient. And again, with the low frequency asymptotic for spherical Hankel and Bessel functions, the Wn, the coefficient, has this expansion polynomial starting from T to the 2n plus 1, and to again the structure we look for is the one with small coefficient WNL, TE and TM. And here is the result. The left column is the one without layer structure, just blowing up a small ball. Then the scattering coefficient is not small. It's like 0.1 the magnitude, but here I add 6 layers, so the unknown is 12, and then doing the optimization to make the scattering coefficient small. So you can see that the coefficient is now 10 to the 9. So the left column is just without layer, and the right column is the 6 layer structure. Then the scattering effect, the cloaking effect is much better. So here, when the rho times omega is 1, you can see that this 10 to the minus 1, and and 10 to the minus 5. But with one adding 6th layer, the cloaking effect is much better. Yeah, that's all I prepared. Thank you.